Well, thanks for having me. I'm Kyle Murray. I'm a researcher at the University of Hawaii, and today I'll share a regional view of crustal deformation in Central East Africa based on 7 years of Sentinel radar data. The goal of the work was to sort of go beyond the relatively sparse GNSS network for a larger scale area and capture a wider range of deformation. We wanted to start to fill in the gaps and understand biases in the current large scale velocity fields, and especially for the shorter wavelength signals that might be hidden within the broader tectonic strain field. So hopefully that will become more clear throughout the talk. But this work was supported by an NSF GeoPrisms postdoc fellowship. So when we talk about measuring active deformation with geodetic tools, we're usually talking about two main methods. So there's GNSS and INSAR. Um, GNSS, Global Navigation Satellite Systems, uses ground-based receivers like this one shown in the image. Uh, they're continuously tracking their position, and it gives you a really precise 3D and time-rich time series of deformation. But the downside is that the network is usually quite sparse outside of certain areas. Um, and so coverage is kind of limited there. That's where INSAR is a powerful complement. Um, this cartoon shows how it works roughly. A radar satellite passes over a region, sends and receives a signal, and then it records a phase of the return signal. And then it comes back later and does the same thing. And by comparing the difference of those two phase measurements, we can measure how the this line of sight vector changes and essentially a proxy for how much change in the ground subsidence or ground motion there was. So in this example, the ground subsided, so the satellite's line of sight increased. And an interferogram is the 2D image showing these relative one-dimensional changes. So this is a great example of such an interferogram. This is from the 2021 eruption of Nyiragongo. You can think of each of these color cycles representing about 3 centimeter contours of ground displacement. And both INSAR and GNSS have been used here to track changes related to migration of magma and volcanic activity. But this really kind of gives you the complete spatial view of what's happening. Um, so we can use this type of data to address a lot of different problems related to active continental extension. I broke some of the main applications up into four categories. And one of the challenges in geodesy is to isolate the particular process that you are interested in, because often there are multiple sources contributing to a given signal. Um, so this work is roughly framed around moving towards improving our understanding of large-scale kinematics and tectonics in East Africa through measurements of the smaller scale non-tectonic deformation. We focused on the central East African rift, where the rift splits into the western and eastern branches. You can see both branches here in the red. Red are representing active faults. Um, and then earthquake epicenters are shown as blue dots and volcanic centers as orange triangles. And then we'll add the gray vectors, which represent crustal velocities from continuous GNSS stations. So far, most geodetic work has either focused on large-scale plate motions using a network of GNSS stations like this, or on localized deformation from a specific rifting event or earthquake, so pretty zoomed in. My goal was to bridge that gap by capturing deformation between these stations and identifying non-tectonic signals at the stations themselves. For example, if any station is affected by a groundwater withdrawal or by volcanic inflation or something like that, those will propagate errors and misinterpret the tectonic signal unless we properly account for those effects. So That's generally what motivated the work. Now, before kind of getting more into the details of our specific study, I just wanted to zoom out and think a little more conceptually about how continents deform. We often picture plate tectonics as large, rigid plates moving past each other with most of the strain concentrated at the plate boundaries. And I think at the global scale, that's a useful framework. But when we look within plates, it gets more complex. We often use block models to describe tectonic motions, treating regions as smaller, rigid plates. But as geodetic coverage improves, we keep needing more and more blocks to explain the data. This suggests that deformation isn't confined to discrete boundaries, and we should instead shift towards a continuum view where a strain is more diffuse and spread across broader areas, even if there are strain concentrations near faults. Although not an extensional zone, a very clear example of this is at the India-Eurasia collision zone. This 2004 study had 45 GNSS stations and found that there were four rigid blocks with deformation concentrated at their boundaries. Later on, a 2017 study analyzed nearly 2,000 GNSS stations, which had been kind of added throughout that time gap, and found they needed at least 30 blocks in order to properly characterize the collision zone with the block model. And there are several studies in between with sort of incremental additions to that. So now let's look back at East Africa. In 2006 study, Eric Calais and others used 10 GNSS stations and found the rift could be characterized by two or three blocks, the Nubian plate to the west and the Somalian plate to the east. And fast forward 15 years, a study by Sarah Stamps used 25 GNSS stations, modeled the regions with five or six blocks. So again, as the data improves, the deformation patterns look more complex. And this kind of work is key to understanding how rifts evolve and where we should focus from a hazards perspective. But I think we're still in the early stages of understanding rift deformation. The GNSS network is still really sparse, and the deformation rates are slow compared to other tectonic settings. And since it's such a challenge to densify the GNSS network across the continent, I'm hopeful that we can start scaling up with other tools like INSAR and even LiDAR to measure deformation across wide ranges, wide scales of spatial scales remotely. So while GNSS has been important for defining plate motion, the large gaps between stations lead to spatial aliasing. So the question is, how is strain distributed across the rift, and how much are these GNSS velocities biased by the more localized or non-tectonic signals? Okay, so our project is a first step towards answering that question. We processed, well, we processed the ascending data from 2015 to 2022 from the Sentinel-1 archive, which is the from the European Space Agency. And we used these five ascending tracks shown with these white rectangles. And that kind of spans from the Kiva Rift to the west up to Turkana Depression to the northeast, and sort of just this entire central area. And I think one of the biggest challenges was just the sheer volume of data. So there's dozens of terabytes just went into the ascending track. We started with the descending track, but ended up not able to hold all that data for our purposes. Um, but that's hopefully going to happen in the future. But we ended up we had to use cloud computing resources through an AWS grant. So that offered a lot of challenges. Another challenge was all the vegetation. A lot of this area is highly vegetated, especially in the west, which can reduce coherence and add a lot of noise to the measurements. So this work required a lot of careful processing techniques, which I will save for a different talk. So the final product is a line of sight velocity field like this map. It's referenced to stable Nubian plate, and um, we also use the GNSS sites to tie in the INSAR deformation and acts as a good reference. And that lets us directly compare with existing tectonic models. So this map is the mean velocity field. It's the blue indicates subsidence and or western motion, and then the red shows uplift and or westward motion. So what jumps out right away is how heterogeneous the deformation is. We see the broad low amplitude gradient from Nubia to Somalia divergence, but it's clearly overprinted by the strong wavelength or the strong short wavelength signals. You can just see all this variation across the entire area. And um, the distribution of deformation really can't be easily modeled by a simple block model. So for the kind of rest of the talk, I'll zoom into some of these different areas and just kind of get a better view of some of these shorter wavelength signals. So first, looking kind of at the tectonic progression across the rift. Um, this is a profile across Lake Turkana Depression connecting a bunch of different GNS stations up there. On the left is the map showing the profile location, and on the top you can see um, the profile path overlaying on the INSAR velocity map. So that's that blue and red again. The panel B shows the eastward component of the GNSS velocities. It's more or less consistent with rift opening at up to about 6 millimeters per year in that section. And on the bottom panel, by projecting the GNSS velocities into INSAR line of sight direction, we can more directly compare the two data sets. And although there is good agreement between the two data sets where they overlap, the INSAR shows much more spatially complex behavior. So the data shows how localized signals can affect the GNSS sites. So for example, this XHOR site here is located in the Chalbi Playa, which is affected by shallow hydrological changes. And so its motion is dominated by non-tectonic processes, which highlights why INSAR is so useful for interpreting tectonic strain. It helps identify and separate out these types of local deformation sources.
Kyle, just a reminder, you're at minute 13.
Sorry, I'm already at 13.
Yeah, yeah. So
Okay. So further focusing on the tectonic signal, uh, our profiles across Kenya Rift quantify the strain distribution. If we assume this is a result of horizontal motion alone, that's about 5 to 6 millimeters per year south of Lake Turkana, and that narrows to 2 or 3 across the Natron Basin farther south. Um, so that's roughly in agreement with previous work that's been done on this. All right, so zooming into the Kivu region, near Gongo volcano, we found the clear deformation pattern. It's associated with a dike intrusion in 2021. Um, and this is approximately 70 centimeters of line of sight displacement in the western lobe and 30 centimeters in the east. And we found potential precursory and post-eruptive deformation. PhD student Derek Marquesi is working on publishing some of those results soon, hopefully. And then moving over back to the eastern branch, Mount Suswa, we can now kind of fully bracket this 2018 to 2019 inflation event, which produced about 9 centimeters of uplift. And our continuous record from our Sentinel data provides a definitive timeline for this transient event and showing that it kind of stabilized after 2019. And then down in the Manyara Basin, we found a previously undocumented deformation source. And so this is a steady uplift of about 4 centimeters per year since 2016 or more. So that's just where our data starts. And that's over an area of about 6 kilometers wide. And so given all the dense kind of volcanism in this area, we interpret it as a potential magmatic or hydrothermal signal. But that'll require some more work to tease out. I'll skip this Holkaria geothermal site because I know that's going to be covered in another talk. And I'll just finish with some data in Nairobi, Kenya. So this is an area where groundwater over extraction is driving subsidence rates up to about 8.5 centimeters per year. Um, and there's kind of this interesting progression where subsidence is propagating from the west to the northeast. And this is a large urban center, and it relies heavily on groundwater. So this is becoming kind of more and more of an issue. And I think INSAR can be a really valuable tool for monitoring groundwater use, as well as the potential negative effects of subsidence on the urban infrastructure. So these signals are an order of magnitude larger than any tectonic rate in the area, and it's a huge source of noise that should be accounted for in any regional tectonic study. So this is another example of where a GNSS site, in this case, the RCMN up in the Northeast, is highly biased by a local non-tectonic process. And that's all I have, and I'll just leave these up. I think we're kind of tight on time, so thank you.
Thank you very much, Kyle. We can take one question.
Thanks, Carl. What are the uncertainties in the line of sight velocity maps, and sort of how long would you need to measure to sort of reliably record, um, the plate tectonic motions in the area from inside?
Yes. Um, that's a great question. It's pretty variable across the rift. A lot of that has to do with where there's a lot of vegetation. Uh, in certain areas, the errors are more or less equivalent to the signal, right? At least a few millimeters per year. The best we can do is kind of around like maybe 1.5 millimeters per year error in the drier areas. And so it does get better with longer time series, but that doesn't necessarily solve the issue. We also need kind of we're going to need multiple sources of data. There's just issues with having a single wavelength that is always interacting with the vegetation. So all the sentinel data is C-band. So we're kind of hopeful as we get more traction on people looking at large scale INSAR studies, we can use the longer wavelengths like ALOS 2 that does a lot better with vegetation, and the upcoming NISAR mission will help fill in these gaps. But I think as we add uh, more different kind of diversity in imagery, we can start to tease out better signals.